All right, so we're going to continue our topic of probability as the basis for insurance. This is the second lesson. Example 1. Using the table below, find the probability that a person has had more than one accident. So we're going to be choosing essentially our notation here. So they don't have letters for greater than one accident. So just for the sake of this, let's use the greater than one. So what is the probability that we have greater than one accident? So if we look in the chart, we can see that that row is this third row here, and we can see that there are 13 total who have had greater than one accident in the past 3 years out of a total of 300 accidents. Okay, so that is 13 over 300, or let's use our calculator. So 13 over, try that again, 13 over 300, or 0.043. 0.043, or a 4.3% chance. So we have a 4.3% chance of having more than one accident in a 3-year time period. Now, automobile insurance companies use this sort of information to make determinations on how much to charge different people, different age groups, etc. Example 2. Using the table below, find the probability that a person has had more than one accident given that they are under 25. All right, so this is a little more specific. So we are going to be looking at, once again, the column more than one accident, but this time we're going to be looking specifically, at the row greater than one, more than one accident, and we're going to be looking at the column under 25. So we want to see essentially, is the probability of me getting in more than one accident higher if I'm in this age group? Okay, so first off, let's talk about the notation. So the probability that we are in more than one accident, and then in probability and statistics, in order to show given, we use a line. We're going to just put a straight vertical line between our statement and our given. And so we want to say given that they are under 25. Now, generally speaking, we would have variables or letters to represent each of these, but this is okay for now. So the probability that they are in more than one accident given that they are under 25. So let's take a look. So because the given is assuming that everyone we're looking at is under 25, we are only going to be looking at that as our total. So this will be the number under 25. So the number of people that got in accidents that are under 25. And then the top number will be the number with more than one accident. All right, so if we look here in our chart, we can see that there are 7 people that got in more than one accident, and of the 100 people that are under 25, which is very simply, sorry about that, 7%. And that's it. All right, so we're going to be talking now about the difference between independent events versus associated events. An independent event is going to be the case when the probability of an event happening is equal to the probability of an event happening given a specific condition. So the probability of one occurring is not affected by the other occurring. So for example, the probability of getting into more than one accident given being 25 is the same as the probability of getting into an accident. We would say that the two events are independent, that my age does not affect the likelihood that I get into an accident. However, if the probability of a given event is not equal to the probability of an event given a specific situation, that means the probability of one occurring is affected by the other occurring. And we would say the events are in fact associated, right? That this S, this given S, For example, in our previous one, given being under 25, if it does not equal the same as the probability of the thing happening by itself, then we say that the one affects the other. Make sure you copy this down into your notes. Now let's take a look at how it works. All right, so example 3. Does the table support the theory that younger drivers get into more accidents? So what we want to do is we want to determine, are the events associated or not? So we want to see, does the probability of having more than one accident, is that equal to the probability of having more than one accident given that I'm under 25? Right? So if we look back to example 1, we already found the probability of more than one accident. We saw that that was a 4.3%. So this here is a 4.3%. And that the probability of getting in more than one accident being under 25 was a 7%. Now, because these are not equal, we're going to say the events are in fact associated, meaning the one does affect the other. So these are associated events, and therefore we could argue that being younger does in fact result in the likelihood that I will get in more than one accident, right? So it is more dangerous to be driving under 25 than for the older groups, all right? So 7% versus 4.3% for everyone. Now, if those had come out equal or approximately equal, we would have argued that the theory that younger drivers get into more accidents is not true. But that did not happen, so we're going to say our theory is in fact true. Justin is doing a statistical analysis of sports cars in his town. If sports cars in his town are involved in more accidents than other types of cars. He polls 315 randomly selected students in his high school, and he gets the results shown in the table below. Does the table support Justin's theory that sports cars get into more accidents? Use the variables given, use the correct probability notation, as shown on the previous slides. Give it a try. All right, so we want the probability here that we have air conditioning, but no manual transmission. Now, the manual transmission is represented by this first circle here. So these are all manual transmissions. And our air conditioning are represented by this circle. And then, of course, the section that is colored with both in our Venn diagram, that's the one that has both. So we're going to be looking at a slightly new notation here. So, all right, so what we're going to do then is we're going to find the probability of A, or air conditioning, and then we're going to subtract the probability of A where it intersects M. So this here is an intersection. Intersection in probability just means the place where both the manual and the air conditioning join together, okay? And that's going to be this here, this 13. So we're going to take the probability of having an air-conditioned car, and then we're going to remove the probability that occurs at that intersection, okay? So we know here that our probability of having an air-conditioned car is 43. Out of, well, we have 135 cars at the show, minus the probability where the intersection occurs, 13, out of 135 cars. So we have 43 minus 13, which is going to give us 30 out of 35. So we have here 30 out of 135. Let's calculate. And that's about a 22% probability. So the probability that a car will have air conditioning but not manual will be a 22%. Now it's your turn to try. Try this. The following Venn diagram describes the cars on the lot of Macachelli's used car showroom. The letter B is used if the car exterior is black, and T is used if the car color is tan. What is the probability that a randomly selected car from Macachelli's lot is not black? Please try to use the correct probability notation. Give it a try. All right, so just a quick piece of advice before you get into practicing this problem. A notation that I need to introduce is the not notation. So if you want to know the probability that something does not occur, we use the notation probability of, for example, let's say I wanted the probability of a car not having a tan interior. We would put P of T, and then we would use this little apostrophe, and that would give us our not. So that little right here, this little apostrophe would be our not. And so that would read the probability of not tan. One other quick note is be conscious of the number of cars on the lot includes all of the numbers shown. Now give it a try.